Welcome back to Entrance and Beyond, and this is day 4 of the DSA series. Today I will be covering the daily question for the day. It's question number 1695, maximum erasure value. So let's dive right in. So the question states, you're given an array of positive integers, nums, and want to erase a subarray containing unique elements. The score you get by erasing the subarray is equal to the sum of its element. Return the maximum score you can get by erasing exactly one subarray. An array B is called a subarray of A if it forms a contiguous subsequence of A, that is, if it is equal to A of L plus 1, all the way up to A of R for some L, comma R. So let's read this question again. So it basically says we're given an array known by the name nums, and we want to erase a subarray containing unique elements. The score you get by erasing the subarray is equal to sum of the elements, and we have to return the maximum score that you can get. So let's look at the test cases. So the first test case is simple. We have an array that has the elements 4, 2, 4, 5, 6. And we basically have to erase a subarray containing unique elements such that the sum of all the elements within that subarray is maximized. So in this case, we can see that if we consider the subarray 2, 4, 5, 6, the sum of this subarray would basically be 17, and that is the maximum sum that we could get. And in the next example, we have another array by the name nums, and the values in that array are 5, 2, 1, 2, 5, 2, 1, 2, 5. And it says the optimal subarray here is either 5, 2, 1, or it is 1, 2, 5. And so the answer would basically be 5 plus 2, that is 7, 7 plus 1, that is 8. And we're going to return that, and then over here constraints are given. So let's understand this question now. So a subarray is basically a contiguous portion of an array, and we have to remove at least one such subarray. So let's look at the first case. So let's just copy this down and let's dive right into this case. So in this case, the approach that I followed was basically a sliding window sort of approach, and that is potentially the best approach to this question because the sliding window approach only takes big O of n time. So sliding window is an important pattern that you should definitely study. So this is just a single question I'm covering today. In the future, hopefully I will be able to cover more such questions. So the approach is simple. We basically need a subarray that contains unique elements, correct? So we need some sort of data structure that would have the ability to track whether a given element is already present in the subarray. If it is already present, we won't add that to the subarray, and then we potentially look at some other subarray because all the elements within the subarray must be unique. That is an underlying condition that is given. So I'll just run through this. I'll do like a dry run, and then hopefully you can understand the logic. And if you don't, there's no worries. I'm going to actually write down the code so that it would make more sense for you. So let's just do the dry run. So suppose we start off at at the number 4. So since there's only one element, we know it has to be unique. So we can say that the current maximum sum is basically 4. Now we're going to go to 2. So we're going to check has 2 appeared or not. So we can clearly see from the naked eye that 2 hasn't appeared. So we can definitely include that because the subarray must have unique elements anyways. So we're going to add this, and now the new sum basically becomes 6, and that would definitely be the maximum value that we have thus far. Now we look at this 4. So when we look at this 4, the problem is that you can see that a 4 has already appeared. So this subarray wouldn't actually be unique. So we must shrink our window, so as to say. So what we can do is we can ignore this 4, and we can consider this 2 and this 4. And if we sum it up, we basically get a 6, and that would be the maximum value thus far. Now we go to the number 5. We can clearly see thus far 5 has not appeared. So it does follow the uniqueness condition. So we can add 5 to the current sum, so we basically get 11, and that would indeed be the maximum. And then when you look at 6 again, it's not present over here. We only have 2, 4, 5. So again, we could add this. Now the new sum becomes 17, and that is actually the maximum sum. So this was just a dry run. Hopefully it did make some sort of sense for you, what we did in the dry run, because it's pretty straightforward. And now we're going to think about it using pointers. So that is what we are planning to do. We're going to use pointers, and we're going to think about it in a sliding window sort of fashion. So it's simple. we basically know that if an element has not appeared yet, we can consider that element in our subarray. So we can say the window is sort of expanding, so as to say. So we're basically going to have 2 pointers. So let's show that. So we're going to have 2 pointers. So the first pointer is going to be our left pointer, and the second pointer that we're going to have is going to be the right pointer. So when the right moves ahead, that basically means our window size increases. And when left moves ahead, we can clearly sort of imagine that the window size is actually decreasing. So that is what we're going to do. So we know one thing: when can we expand the window? So the question is, when can we expand the window? So that is the main question. So we can either expand the window or we can shrink the window. There are only 2 options that we have at this point of time. We either expand the window or we end up shrinking the window. These are the 2 options that we have. Now, the only thing we have to understand in this question is when to expand and when to shrink. So we can clearly understand that if an element is not present in the current subarray, we have to expand because we are looking to maximize the value. And I think it was given all the values are positive, so we know adding a new element would definitely increase the sum that we have for the subarray. So we're going to simply expand when we know the new element that we have to add, it's not already present in the subarray. And we can shrink if the new element that we're trying to add is already present in the subarray. So we must basically shrink our window till the window only contains unique elements. So let's dive into this approach with the left and right pointer. So since we want to track whether a number has appeared in the subarray or not, there are 2 main data structures that we could be using in this case. So the first one is a set. So set basically stores only unique values. So what we can do is we can just check whether a value is present in the set. So suppose we are at this 4. So we could just simply check, we could do the .find method to find whether 4 is actually already present in the set. And since it is, we know that now we have to shrink our window. But the only problem with the set approach is that we'd have to remove things explicitly from the set. So it's not really the best sort of data structure that we can use in this question, and also not the most suitable data structure to use in other questions. And so now you can probably guess it. The other data structure that we can use is basically a map. So map, and we're going to store the frequency of each element. So you can intuitively think about it in simple terms that in a given window, the frequency of a given element, or the frequency of all the elements, must be 1. So that would mean that all the elements are unique. So we're just going to store a map that stores the frequency of each of the elements. And based off of that, we'll get an idea whether the new element should be added to the current window or it shouldn't be added to the current window. So whether we have to expand or we have to shrink. So now that would probably make more sense to you. So let's dive right in. So first of all, we're going to start off at 4. So our right pointer is where we're going to start off at. So this is where we are going to start off at. We're going to start off at our right pointer. So we can see 4. So 4 is not present in the map. So, or we can say 4's frequency is essentially 0, because by default the frequency of elements is 0. So 4's frequency is 0. So what we can do is we can take its sum. So we're going to take its sum. So current sum becomes 4 and maximum sum becomes 4. Now what we can do is we can now simply move this R ahead. We can simply move this R ahead. That is what we're going to do. We're going to take this R, we're going to move it ahead. Now we look at 2. So the frequency of 2, again, it's not present anywhere. So we can clearly say that 2 is going to get included. So I'm going to show the current sort of unordered map that we have, just so that it's a bit more clear and you have an idea of what's happening. So by default in C++, maps basically are mapped to 0. So if like we haven't explicitly assigned a value, that is what's going to happen. So we have 4, 2 would basically be assigned to 0, 5, and 6. Now this isn't like the backend sort of implementation we have. I'm just using it so that you can visualize the question better. So now what we're going to do, we can simply see that. Now again, so we started off at 4, like I told you. So we start off at 4. So 4's frequency is 0. So we can add that. So again, the current sum becomes 4. And let's just store the maximum sum. I won't like be showing the current sum because it's not needed. You probably understand that. So now the frequency of 4 becomes 1. Now we come to the next element, 2. Okay, now 2's frequency is 0. Now its frequency will become 1. And the new maximum sum that we have is going to be 6. So 4 plus 2 is 6. Now we can again move this right ahead. Now 4 already has a frequency of 1, so we know we have to shrink now. So we're gonna basically what we're gonna do is from the sum we're gonna remove this element. So our current sum would basically be 2 right now, because this is the current sum, right? So current sum is 2. So this would convert to 2, and again this is the maximum that we have is 6. So now what we can do is we can move the left pointer ahead, and now we can see that we're just gonna subtract. We're gonna decrement the count of this left variable. So 4's count would now become 0. So now we're pretty much good to go. Now this 4's count would again translate back to 0, and the current sum is 2. The left pointer is gonna move ahead. Now we're done with the shrinking part. Now we can basically, we're gonna check R again. So again R is now unique, as you can see. So the new sum again becomes 6. We're gonna move R ahead. Now we're gonna check for 5. It is again unique, so we're gonna increase its frequency. New sum becomes 11, and then we're gonna also move R to the last index, and again the value that we get is 17. So hopefully this did make some sense, and if it didn't, you can put it down in the comment section, and I'll try to maybe re-explain this question. So I think you got the intuition how to solve the question. So if you have a pen and paper, if you're on LeetCode, first of all, try to go through this video and try it yourself. And if you still aren't able to write the code, and then I think it's a good time to come and watch me code it. So you can take a pause and try to solve the question. Now let's dive right in. So we need a variable to store the maximum score. So the maximum score, suppose, is max score, and we set it up as 0. Start off with, we need a left pointer that's going to be set to 0. We need a right pointer that's going to be set to 0. And then we need something like a current score to track out the score that we have right now for the given window. We're going to set that as 0. And now we're going to start. So we're going to run a simple loop while left, or we can say while right is less than nums.size. What are we going to do? So first, okay, we need a unordered map as well. So unordered map is what we are going to end up taking. Once we have the unordered map, we know it's going to be a frequency map, so the keys would be integer representing the number, and the value would be the int representing the frequency of that given number. So I'm going to run right into the code now. So now we have the while loop, so we're going to check if the frequency of nums of r, if it is equal to 0, in that case we know that we have to expand our window. So first of all, we're going to do current score plus equal to nums of r. Then we are going to do frequency of nums of r plus plus, and that is pretty much all. And yeah, we're going to increment r as well. This is if the else condition would basically mean if an element is already present in the set, or already present in the map, sorry. So if its frequency is anything greater than 0, we can say it is already present in the map. Now this is a shrinking phase. So our current score now would basically be, we're going to subtract nums of left, because we know left is used for shrinking our window. So we're going to subtract that. And after that, what we're going to do is we're going to do frequency of nums of left. We're going to subtract 1 from it. So minus minus in C++, and then we're going to do L++. And in the end, we can compute maximum. So max score is equal to max of max score, comma, current score. So once this loop is done, we are going to just return the maximum score, and let's see if it runs all right or not. It should run all right because we have gotten the logic clear. So as you can see, we get the appropriate result, and this takes a big O of n time. And within this, there are some variations where you can actually move L to the left. Like, you don't have to move a single element at a time. You can use a while loop for that as well. But I haven't really shown that. You can try that out. It's not that tough. So hopefully this question did make sense. And if it didn't, please either DM me on LinkedIn, reach out to our channel, or you can even drop down a comment. So do drop down in the comment box other questions that you want to be discussed, and do give me some feedback just so that I understand whether things actually are becoming clear, and if they're not, why they aren't becoming clear. So thank you so much for tuning in. Bye.